This is fifth module of chapter 5. In previous modules of this chapter, we have described different methods to find the inverse of a matrix. In these methods, it is assumed that the matrix must be non-singular and square. Obviously, a non-singular matrix is a square matrix. But in many applications, we have seen that the inverses of singular and rectangular matrices are essential. So, a new kind of inverse called generalized inverse or G inverse is defined and explained with some examples. So, this module is devoted to generalized inverse of a matrix. Let A be a matrix of order m by n. The generalized inverse of an m by n matrix A is another matrix capital X of order n by m. That means the generalized inverse of a matrix and its order are reversed. Unlike conventional inverse, the generalized inverse are of different types depending on shape, singularity and requirement. Different authors define different type of G inverses. The G inverse has a special importance if the matrix is either singular or rectangular. If the matrix is non-singular, then G inverse is nothing but the conventional inverse. If it is a non-singular matrix, then there is no need to determine G inverse because for that matrix the conventional inverse exists. Now, we define certain terms which are associated to G inverse. Let A be a matrix, it may be a rectangular matrix or it may be a singular matrix or it may be a non-singular square matrix. Now, we define four equations. The first one is AXA equal to A. Second equation is XAX equal to X. Third equation is AX equal to AX star, where star represents the conjugate transpose of the matrix. The fourth one is XA equal to XA transpose conjugate transpose. Now, depending on this definition, we can define different kind of generalized inverse. The matrix capital X is called a generalized inverse of A denoted by A minus if the equation 1 holds, and it is called a reflexive generalized inverse of A, and that one is denoted by A r minus if the condition 1 and 2 hold. The matrix X is called a minimum norm inverse of A denoted by A m minus if the condition 1 and 4 hold, and the matrix X is called least square inverse of A denoted by A l minus if the condition 1 and 3 hold, and if the conditions 1, 2, 3 and 4 hold, then the matrix X is called the more Penrose inverse of A, and that one is denoted by A plus. Among these G inverses, only the more Penrose inverse A plus is unique and all other inverses are not unique. So, the more Penrose inverse is important compared to the other generalized inverses. If the matrix A is square and non-singular, then all these inverses reduces to the conventional inverse A power minus 1. Since the more Penrose inverse is unique, so it is widely used in many applications such as to solve a system of linear equations. Now, we introduce some important properties of more Penrose inverse. The first one is A plus of A plus equal to A, that means the more Penrose inverse of a matrix of the more Penrose inverse is equal to the same matrix. This is similar to the conventional matrix inverse. And second property is the more Penrose inverse and its transpose is equal to the inverse of the transpose of the matrix A. This is also the same as in conventional matrix inverse. If the matrix A is non-singular and square, then the Moore Penrose inverse is equal to the conventional matrix inverse. In general, the Moore Penrose inverse of the matrix AB is not equal to the Moore Penrose inverse of the matrix B into the Moore Penrose inverse of the matrix A. This property is also similar to the conventional matrix inverse. Let A be a matrix of order m by m, not necessarily singular, and AT represents the transpose. Then if the rank of the matrix A is 0, then Moore Penrose inverse of A is a null matrix of order n by m. If the rank of the matrix A is 1, then the Moore Penrose inverse of the matrix A is given by this formula, that means 1 by trace A into A transpose whole into A transpose, where trace represents the sum of the diagonal elements. And third property is, if the rank of the matrix A is n, then A plus equal to inverse of the conventional inverse of AT into A whole into AT. And if the rank of the matrix A is m, then the Moore Penrose inverse of A equal to A transpose into the conventional inverse of A into A transpose. Now, the generalized inverse can be used to solve a rectangular system of equations. The G inverse A plus of the matrix A is used to solve the following system of equations: Ax equal to B, where B is a non-null vector and the matrix A is of order m by n, and x is a vector, the unknown vector of order n by 1, and B is the known vector of order m by 1. The solution of the system of equation Ax equal to B is given by the formula x equal to A plus B, where A plus is the Moore Penrose inverse of the coefficient matrix A. Now, this solution obtained in equation 7 is least square solution. It can be shown that the Euclidean norm of a vector is minimum. A solution extra of the system of equations Ax equal to B is called least square solution if Ax star minus B is not equal to 0, that means this is a non-null vector, but the norm of the vector Ax star minus B must be minimum. That is, the least square solution minimizes the Euclidean norm Ax minus B for an inconsistent system of linear equations. Now, we present a very efficient method to find the Moore Penrose inverse. That method is known as Greville's algorithm. So, it is recursion algorithm, that means the Greville's algorithm is a recursion algorithm, and this algorithm is used to find the Moore Penrose inverse of a rectangular matrix of order m by n. Let A be a rectangular matrix of order m by n, that means the matrix contains m number of rows and n number of columns, and this matrix is denoted by n column vectors alpha 1, alpha 2 up to alpha k dot 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 alpha n, where alpha k, the kth column of the matrix A, is a column vector and the elements of this column are a1k, a2k up to amk. So, using this notation, we can determine a submatrix constructed by the first k columns of the matrix A, that one is denoted by ak, that is ak equal to alpha 1, alpha 2, alpha k, that means a submatrix formed by the first k columns of the matrix A. Also, this matrix AK can be written recursively as AK minus 1 alpha k, that means AK is a submatrix containing the first k minus 1 columns and it is augmented with the kth column. Since the Greville's algorithm is recursive, So an initial condition is required to perform this algorithm. If alpha 1, that means the first column vector of the matrix, is 0, then A1 plus equal to 0. A1 plus is the matrix submatrix obtained from the matrix A by considering only the first column. Otherwise, A1 plus equal to alpha 1 transpose into alpha 1 whole inverse of this matrix into alpha 1 transpose. So, this is the initial condition for the Greville's algorithm to find the inverse of the matrix A. Now, we define the column vectors, two column vectors, one is called delta k and other is called gamma k, that are defined below. The delta k equal to the Moore-Penrose inverse of the submatrix A k minus 1 into alpha k, and gamma k is defined as alpha k minus 1 into delta k. Now, another vector beta k is defined as, if gamma k not equal to 0, then beta k is equal to gamma k plus. So, gamma k plus is the Moore-Penrose inverse of the matrix gamma k, which is equal to the conventional inverse of gamma k t into gamma k whole into gamma k transpose. Otherwise, beta k equal to 1 plus delta k transpose into delta k whole inverse into delta k transpose into the Moore-Penrose inverse of the matrix A k minus 1. Then the Moore-Penrose inverse of the submatrix A k, that means A k plus of the matrix A k, is computed as A k plus equal to a matrix containing two rows. The first row is A k minus 1 plus minus delta k into beta k, and second row is beta k. This process is continue for k equal to 1 to up to n, where n is the number of columns of the matrix A. So, we have defined different types of generalized inverse, and we have seen that these type of generalized inverses are applied for all types of matrices, that means for singular matrices and also for rectangular matrices. And we have mentioned that if the given matrix is non-singular and square, then all these generalized inverses become the conventional inverse of the matrix. Also, we have described the Greville's algorithm to find the generalized inverse of a matrix. The matrix may be singular or rectangular. Now, we will illustrate the Greville's algorithm with the help of two examples. Let us consider the following matrix to find the Moore-Penrose inverse, that means the G inverse. And using this inverse, G inverse or Moore-Penrose inverse, we have to solve the following system of rectangular equations. Note that this system of equations contains 3 equations and 4 variables. For this problem, the vectors alpha are alpha 1 equal to 0, 1, minus 1, alpha 2 is 1, 0, 2, alpha 3 is 0, 2, minus 1, and the last vector alpha 4 is 2, 1, 0. Here A1 equal to alpha 1 equal to 0, 1, minus 1, that means A1 is non-singular or non-null matrix. Therefore, A1 plus, that means Moore-Penrose inverse of the matrix A1 is alpha 1 t, alpha 1 whole inverse in conventional sense into alpha 1 t, and the alpha 1 t is equal to 0, 1, minus 1, alpha 1 is 0, 1, minus 1, and we have to determine the inverse of the product of these two matrices into 0, 1, minus 1. The row vector, that one is nothing but alpha 1 t, and after simplification the matrix A1 plus becomes half into 0, 1, minus 1. So, 0, half, minus half is the first G inverse of the matrix of the submatrix A1. Now we go to the second iteration. In second iteration, we have to calculate the first vector, or we can say that this first vector as delta 2, and delta 2 equal to A1 plus into alpha 2, and A1 plus is nothing but the row vector 0, half and minus half obtained in first slide, and alpha 2 is 1, 0, 2. After multiplication or product of these two row and column vector, we obtain a matrix of order 1 by 1, and that one is minus 1. Now we calculate the another vector gamma 2, which is equal to alpha 2 minus A1 into delta 2. After substituting the values of alpha 2, A1 and delta 2, we obtain the column vector gamma 2, which is equal to 1, 1, 1, and obviously it is a non-null vector. Hence we calculate the another vector beta 2 equal to gamma 2 plus. Gamma 2 plus is the more Penrose inverse of the vector gamma 2, which is equal to the conventional inverse of the matrix gamma 2t into gamma 2 into gamma 2t. After simplification, this vector beta 2 becomes a row vector which is equal to 1/3, 1/3 and 1/3. Now delta 2 beta 2 equal to minus 1/3, minus 1/3 and minus 1/3. This is a row vector. So A2 plus, that means the more Penrose inverse of the submatrix A2 is equal to a matrix whose first row is A1 plus minus delta 2 beta 2, and second row is the vector beta 2, and which is equal to a matrix of order 2 by 3 whose first row is 1/3, 5 by 6 and minus 5 by 6, second row is 1/3, 1/3 and 1/3. Now we go to third iteration, that means we calculate the column vector delta 3, which is equal to A2 plus into alpha 3. After simplification, this vector becomes a column vector whose first element is 11 by 6 and second element is 1 by 3. Now we calculate the vector gamma 3, which is equal to alpha 3 minus A2 into delta 3. Again, after simplification, this vector becomes a column vector whose elements are minus 1/3, 1 by 6 and 1 by 6. This is also a non-null column vector. Hence, the beta 3 equal to gamma 3 plus, which is equal to the conventional inverse of the matrix gamma 3 transpose into gamma 3 whole into gamma 3 transpose. After simplification, this reduces to a row vector whose elements are 6 into minus 11 by 3, 1 by 6 and 1 by 6. And again, after simplification, it reduces to a row vector whose elements are minus 2, 1, 1. So this is the beta 3. Now we calculate the matrix delta 3 beta 3, and after simplification this becomes a matrix of order 2 by 3 whose first row is minus 11 by 3, 11 by 6, 11 by 6, and second row is minus 2 by 3, 1 by 3 and 1 by 3. Therefore, the third iterated matrix is A3 plus equal to, the first row is A2 plus minus delta 3 beta 3 and second row is beta 3, which is equal to a matrix of order 3 by 3. First row is 4 minus 1 minus 2, second row is 1 0 0, third row is minus 2 1 1. So this is the third approximated or third iterated more Penrose inverse of the matrix A. Now we go to the last stage or the fourth stage. Here we calculate the vector delta 4, which is equal to A3 plus into alpha 4. After simplification, this vector becomes 7 2 minus 3, and the vector gamma 4 equal to alpha 4 minus A3 into delta 4. After simplification, it reduces to a null column vector 0 0 0. Thus, the vector beta 4 is calculated by the formula inverse of the matrix 1 plus delta 4t into delta 4 into delta 4t into A3 plus. So, after simplification it reduces to 1 by 63 into a row vector whose elements are 5, 1, 7, and it is equal to 5 by 63, 1 by 63, 1 by 9. Then delta 4 beta 4 equal to the product of the column vector 7, 2, minus 3 and the row vector 5 by 63, 1 by 63, 1 by 9. After simplification, it becomes a matrix of order 3 by 3 whose first row is 5 by 9, 1 by 9, 7 by 9. Second row is 10 by 63, 2 by 63, 2 by 9, and third row is minus 5 by 21, minus 1 by 21, minus 1 by 3. Hence, we calculate A4 plus, that means 4 iterated inverse more Penrose inverse of the submatrix A4, which is equal to A3 plus minus delta 4 into beta 4, and second row is beta 4. So, after substituting the values of all these elements, we obtain a matrix of order 4 by 3 whose first row is 31 by 9, minus 10 by 9, minus 25 by 9. Second row is 53 by 63, minus 2 by 63, minus 2 by 9. Third row is minus 37 by 21, 22 by 21, 4 by 3, and last row is 5 by 63, 1 by 63, 7 by 63. And this is the last step, and hence the A plus, that means the more Penrose inverse of the given matrix A, is equal to A4 plus, and which is given by this matrix, and note that it is a matrix of order 4 by 3. The given system of equations can be written as Ax equal to B. Note that the coefficient matrix for this problem is a rectangular and its inverse is A plus, not A minus 1, not the conventional inverse, because the matrix is a rectangular matrix. Thus, the solution of the given system of equations can be obtained by the formula x equal to A plus B, that means more Penrose inverse into B. Thus, x equal to A plus into the vector B. After multiplication, the vector x is minus 13, minus 2, 8 and 0. Hence, the required solution of the given system of equation is x1 equal to minus 13, x2 equal to minus 2, x3 equal to 8 and x4 equal to 0. So, this is the solution of the given system of equations containing 4 variables and 3 equations. This is a very interesting problem. Note that a system of 3 equations and 4 variables is solved by using the concept of G inverse, and obviously it is not possible by using the conventional inverse, because the conventional inverse of a matrix is not available or applicable for a rectangular matrix. It may be verified that A plus satisfies all the conditions of 1. Again, A3 plus equal to A3 minus 1. A3 minus 1 is the conventional inverse of the submatrix A3, because for this submatrix A3 the determinant is minus 1, that means A3 is a non-singular square matrix. And also for this matrix A into A plus is equal to I4, that means a matrix, unit matrix of order 4 by 4. But A plus A, that means the product of more Penrose inverse into the matrix A, is this matrix, it is a matrix of order 4 by 4. Note that this matrix is not the unit matrix of order 4 by 4. Now we consider another matrix to find the more Penrose inverse and note that this matrix contains a null column vector, that means the first column is a null column vector, and use this matrix to solve the following system of equations. Here alpha 1 equal to 0 0 0, that means a null column vector, alpha 2 is 1 1 0, alpha 3 is 0 minus 1 1, and the last column vector is 1 1 2. Since alpha 1 is a null column vector, therefore A1 plus is a null row vector. This is the initial Moore-Penrose inverse of order 1. Obviously, delta 2 equal to A1 plus into alpha 2, and after simplification it reduces to a matrix of order 1 by 1 and its element is 0. Now, the gamma 2 equal to alpha 2 minus alpha 1 into delta 2, which is equal to alpha 2 equal to 1 1 0. Therefore, beta 2 equal to inverse of gamma 2 t into gamma 2 t. After simplification, this vector, the vector beta 2 becomes half half 0. This is a row vector, and delta 2 beta 2 equal to a row vector whose elements are 0 0 0. Now we calculate A2 plus, which is equal to A1 plus minus delta 2 beta 2, and second row is beta 2, and it is equal to a matrix of order 2 by 3. First row is null row vector whose elements are 0 0 0, and second row is half half 0. Now we go to the third iteration and we calculate the vector delta 3, which is equal to A2 plus into alpha 3, and it is a column vector containing two elements 0 and minus half. Then gamma 3 equal to alpha 3 minus A2 into delta 3. After simplification it becomes a column vector whose elements are half minus half and 1. Therefore, beta 3 equal to the inverse of gamma 3 transpose into gamma 3 transpose. After simplification, this row vector becomes 1/3 minus 1/3 2/3, and the matrix delta 3 into beta 3 equal to a matrix of order 2 by 3 whose first row is 0 0 0 and second row is minus 1 by 6, 1 by 6 and minus 1 by 3. Therefore, A3 plus equal to a matrix of order 3 by 3 whose first row is 0 0 0, the null row vector, second row is 2 by 3, 1 by 3, 1 by 3, and third row is 1 by 3, minus 1 by 3, 2 by 3. Now, delta 4 equal to A3 plus into alpha 4. After simplification, this column vector is 0, 5 by 3, 4 by 3, and the vector gamma 4 equal to alpha 4 minus A3 delta 4, which is equal to minus 2 by 3, 2 by 3, 2 by 3, a column vector. Finally, beta 4 equal to inverse of gamma 4 t into gamma 4 t. After simplification, this row vector becomes minus half half half. Therefore, delta 4 into beta 4 is a matrix of order 3 by 3 whose first row is 0 0 0, second row is minus 5 by 6, 5 by 6, 5 by 6, and third row is minus 2 by 3, 2 by 3, 2 by 3. Therefore, A plus, that means the Moore-Penrose inverse of the matrix A, is equal to A4 plus. This is the last step. So, A plus is equal to A4 plus, and which is equal to a matrix of order 4 by 3 whose first row is 0 0 0, second row is 3 by 2 minus half, third row is 1 minus 1 0, and fourth row is minus half half half. So, this is the final Moore-Penrose inverse of the given matrix A. Note that the first row of this matrix is a null row vector, whereas the first column of the given matrix was the first null column vector. Now, the given system of equations can be written as Bx equal to small b, where B is the coefficient matrix whose elements are 1, 0, 1, second row is 1, minus 1, 1, third row is 0, 1, 2, and B is the right hand vector whose elements are 3, 2, 1. If we add a 0 column vector at the beginning of the matrix B, then the augmented matrix becomes the matrix A. Actually, we have already calculated the generalized inverse of the matrix A. So, we use the generalized inverse of the matrix A to solve this system of equations. Thus, the augmented matrix A equal to 0 B dot B equal to a matrix of order 3 by 4 whose first row is 0, 1, 0, 1, second row is 0, 1, minus 1, 1, third row is 0, 0, 1, 2. And hence the solution of the given system of equations can be obtained by this formula x equal to a plus b, where first matrix is the Moore Penrose inverse of the matrix A and second column matrix is the matrix B. After simplification, this column vector reduces to 0, 3, 1, 0. Hence, the required solution of the given system of equation is x1 equal to 3, x2 equal to 1, x3 equal to 0. Note that the first element of this column vector is discarded because the first row of A plus is corresponding to the first column of the matrix A. So, this is the final solution, and this solution is obtained with the help of Moore-Penrose inverse of a matrix. In this module, we have defined a new kind of inverse called generalized inverse, and generalized inverse can be determined for any kind of matrices. It may be a singular matrix or it may be a rectangular matrix. The generalized inverses become the conventional inverse if the matrix is non-singular. We have mentioned that the Moore-Penrose inverse is unique and it is useful in many applications. So, we have described a method to find the Moore-Penrose inverse. Also, we have solved a system of rectangular equations using the generalized inverse or particularly Moore-Penrose inverse.